All right, guys, Math 6, Day 10. Let's take a look. Today we're going lessons 38, 39, and 40. So let's go ahead and head over. So lesson 38, we're adding and subtracting decimal numbers and whole numbers. So we just worked with place values and then adding and subtracting decimal numbers earlier. So we're going to be working with that times where we have decimal numbers and whole numbers. And then we're going to introduce squares and square roots. Not squares the shape, but squares as far as using exponents and square roots. So we'll show you what that means. And then there's a way that we can use the calculator for that, which I will show you when we get further down the road. All right, so if paper used in school is often 11 by 8.5 or 8.5 inches, find the perimeter of a sheet of paper by adding the lengths of the four sides. Okay, well, we're going to have a rectangle. All right, so we're going to add 8.5 by 8.5 and then 11. Again, we can write as 11.0. So including that decimal, we don't have to, but when we have that, it just helps us, again, as we worked earlier or in the previous few lessons, when we line up that decimal, then every other place value is automatically lined up. If we forgot and we moved this, that's supposed to be in the tens place under 8 and this one under the 5, that's going to throw off our whole calculation. We're going to get a much different perimeter than we should be getting. And again, we're adding this, we're finding the perimeter, so we're adding up all four sides, nothing different. So 5 plus 5 plus 0 plus 0 is 10. Carry the 1. So I get 9 plus 8 is 17, 18, 19. And then carry that 1 up there because it's 19. 1, 2, 3. Okay, and then we carry down our decimal to the place right there. So we get 39.0, or if we didn't want to write it with that decimal, since it's a whole number, we can, or we can just rewrite it as 39 and its perimeter, so inches. Okay. Okay, when we're subtracting, same thing, 12.75 minus 5. Okay, we'll call it 5.0. We can even call it 5.00 if we want to see two decimal places, just to make it visually more appealing as we calculate it. Okay, but make sure that the ones place lines up, even though we didn't have decimal places, it was just 5. We went ahead and filled them in. We don't have to, but it's easier to say 5 minus 0. Either way, we're just bringing that 5 and that 7 down. Okay, and then we have 2 minus 5, which is a negative number. So now 12 minus 5, which is 7. Okay. So again, if there's no decimal, we can write any number as a decimal number. We just add, so like if we have 123, well, we can write that as 123.0. We usually don't unless we want to see the decimal for calculation purposes, but we can include that. We can write any number as a decimal number, just like we can write any number as a fraction. 123 over 1, now it's a fraction. Okay? 123.0, now it's a decimal number. So just because sometimes we see numbers as mixed numbers, whole numbers, decimal numbers, it doesn't change anything. We can still perform whatever calculation we need to. Okay, now something new that we've talked a little bit about, I think we've seen a few examples so far, but we have exponents. So as part of our order of operations, we have grouping symbols, or usually we say parentheses, and then exponents. And it's really exponents or any square roots, because those go hand in hand, just like addition and subtraction work together, and then multiplication and division work together. So a square, and it does come, the term does come from the shape of square because we know the side lengths. If it's 5 and 5, well, square 5 times 5 is 25. So 5 squared, quote unquote, is 25. So we can write it as 5 times 5, or since we know it's the same number, we can say 5 times 5 is the same as 5 to the power of 2. 5 to the second power, or 5 squared, either way. And we just say squared for an exponent of 3. The small number in the upper right-hand corner is called the exponent. If it's 3, we can say, whatever number, 5 to the power of 3, or 5 cubed is what we say. Because if we have a square that's three-dimensional, it's now a cube, but we'll talk more about that down the road. The ones you see today will probably be mostly working with squares and square roots, just to kind of introduce them. If we have this right here is what we call our base. So the larger number, so as we write it, we want to be, make sure we know what we're writing. If I just write it kind of like this, is that, is that 52 or is that 5 to the power of 2? Okay, so make sure your handwriting, you're able to distinguish, okay, this is a smaller and it's in the upper right-hand corner. Okay, so now it's pretty obvious that this is smaller, it's up above, so this is saying 5 to the power of 2. Okay, so we do 5 times 5. I have 2 5s. If it was 5 to the power of 4, then it would be 5 times 5 times 5 times 5. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so this is what we call the base, whatever number or unknown or whatever it is. That's the larger portion down here. And then this is what we call the exponent. There's a bunch of rules of exponential equations and different things off of whether or not they're the same base, which we'll talk about down the road. For right now, just know this is the base, this is the exponent, and then this is the calculation that we're doing when we have that. So if example 3, we have what is 12 squared? Okay, well, 12 squared, or 12 to the power of 2, or 12 times 12 is 144. That's our multiplication table. When we simplify, again, we do exponents before addition in our order of operations. That's because we can't call this 7 to the power of 2 or 7 to the power of 4 or something like that. That would give us a totally different answer than what we're doing. So we do the exponents first. So 3 squared is 9. 4 squared is 16. And then we have 9 plus 16 equals 25. Okay, so 3 times 3, or 3 squared, is 9. 4 squared is 16. And then after we've done the exponents, then we add them. Okay. Now, kind of the inverse of squares or any exponents are roots. And the inverse of a square is a square root. So if we know, for example, that 6 is the example they use here. So if we know that 6 squared, or 6 times 6, is 36, well, then we can work backwards from that. If we see something like this little symbol that almost looks like a division box, but it's got kind of this leg sticking out here, this is called a radical sign, or in this case, a square root. We could put the 2 right there. This is a square root, or we could draw it without that in there. And I'll show you how we can do these on our calculator. There's a button that makes it easier as we get into some more complex ones. We can even do, cubed roots. If we have something like that, there's a 3 right there. This is saying what number to the power of 3 equals 27. But we'll just stick with the squares and the square roots. So 6 squared is 36. Well, then kind of working backwards from that, the square root of 36 equals 6. Because this is saying, well, what number squared equals 36? And it's going to work backwards to be 6. So that's where knowing some of your 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And just remembering some of these off of our multiplication table or what we've covered, 36 and so on. 7 squared is 49. 8 squared is 64, 9 squared is 81, and 10 squared is 100, 11 squared is 121, and 12 squared is 144. And that means if it's a perfect square, like these numbers are, not all numbers are, but these ones are, so we can work backwards and say, well, 4 squared is 16, so the square root of 16 is 4. Okay, so we can go from 4 squared to 16, or square root of 16 equals 4. Okay, so if we have the square root of 64, in this example here, where the square root of 64, we just said 8 squared equals 64, so the square root of 64 has to equal 8. Okay, so that's where knowing multiplication tables and some of these are going to help you out. We can also calculate these in our calculator, but you'll get to where a lot of them you just have them kind of memorized through practice. Okay, practice that we'll do together when we return. Okay, lesson 39, we're looking at multiplying decimal numbers. So if we have, for example, a rectangle that we have decimal numbers, it's still the same process, length times width. We still have to multiply those two numbers. Hey, we can do it. We can do it by making them all fractions and then multiplying and then simplifying. I think it's a little bit easier to just multiply them out like we would any other numbers, and then I'll show you how we account for it at the end. So we can say 75 hundredths times 5 tenths, 10 times 100 is 1,000, 75 times 5 is 375. 375 thousandths, we can write as a decimal. So that's absolutely not incorrect to do it that way. You can do it that way. It's just we're making it from a decimal to a fraction back to a decimal. So I think it's a little bit more work. So what I would do is I would say, just like when we have 2-digit numbers, in this case, we don't have to line up the decimal values like when we add, and I'll show you why here in a second. So what I would do is I would just like we have 2, 3, 4-digit numbers, we stack them on top if we're doing it by hand. Okay, and then we multiply, we start here and we multiply by the ones place, then the tens place, and we only have one number down here, so we don't have to go down to a second row. So 5 times 5 is 25. Okay, so I don't put in 25, I just put the 5 and then the 2 up here, and then 7 times 5 is 35 plus 2 is 37. Now it's not 375. Then we go in and we count the decimal places. I have 1, 2, 3. Since I have 2 decimal places here and 1 here, that accounts for 3 decimal places. So I start here with the decimal and I go 1, 2, 3 and fill it in. So I think that way is a little bit easier and saves a little bit of time. It's the same thing. If you'd rather make it into a fraction and then use that fraction to work backwards to figure out what the decimal number would be, I would just set it up like, if it was 75 times 5 without the decimals, it'd be 375. We'd do the same thing. But now we have 75 hundredths times 5. Sorry, this was multiplication. Don't forget that. Times 5 tenths, okay, or 0.5, and then we multiply it out and then account for the decimal at the very end. So let's look at example 2 because it uses what we just learned about exponents. So if I have 2.5 squared, okay, parentheses, 2.5 squared, well, I'm going to do 2.5 times 2.5. Okay. So again, we're not adding, so we don't need to drop down the decimal right now. We'll account for 1, 2 decimal places at the very end. 5 times 5 is 25. 5 times 2 is 10 plus 2 is 12. And then we're moving over a place value, so we add a 0 right here. 2 times 5 is 10. 2 times 2 is 4, plus 1 is 5. And this is 5 plus 0, 2 plus 0, 1 plus 5. So 625, but now we have 1, 2 decimal places. So start here, 1, 2, and we get 6.25. If you wanted to do it as, this one would be really tough to do as a fraction, because we do 2 and 5/10. We'd have to make it an improper fraction, and then we'd have to multiply them both and then simplify it and then convert it back to a decimal. So I think going to be easier to use this method than always using the converting it to a fraction. Okay, practice set. We will go over those as a group when we return. Then lesson 40 is using 0 as a placeholder, and then circle graphs. So using 0 as a placeholder. So when we're subtracting 0.5 minus 0.32, 0.2 times 0.3, or 12 cents divided by 3. So we've worked with this already. We're just kind of doing it again, or giving a more exact name to it. Whenever we have blank spaces, and we fill in zeros. So if we have 0.5 minus 0.32, and we're going to add that 0 to the end. 0.5 and 0.50 are the same number. We're just adding a 0. So now we can start to calculate when we subtract. Okay, so we do our subtraction. This becomes 10 minus 2, which is 8. We borrowed 1 from 5, so now it's 4 minus 3, which is 1. Decimal is lined up because we're subtracting, and then 0 minus 0, we still just have a 0 there. Okay, so if we have 3 minus 0.4, okay, again, 3.0, we're going to call this, minus 0.4. So 3, and then so it was 3, but we know, as we talked earlier, we can write it as 3.0, and then 0 minus 4. I can't do that. Well, I can, but it's negative, so then I have to borrow 1 from here. So that's 10 minus 4, which is 6. 2 minus 0, which is 2. And then just carry that decimal place down. So just make sure the decimal place lined up, and then anywhere you have a blank space, you can add a 0 to help us as we calculate. So it just makes it easier to write in a decimal instead of 3 minus 0.4. We're going to call it 3.0, which is the same thing, but now it's a little bit easier to do the subtraction. And if we have 0.2 times 0.3, again, sometimes I just write it as 0.2 and 0.3, but either way, we can write in those zeros if we want to. It's the same thing. If there's nothing out there, as I said, that blank spot is implied 0. So we can write it in, or we don't have to. If I go 0.2 or 0.2 times 0.3, well, 3 times 2 I know is 6. And then 3 times 0 and 0 times 2 and 0 times 0. It's just going to be all zeros. So 3 times 2, 3 times 0, 0 times 2, 0 times 0. So I'm left with 6. And then these zeros, or if they were blank spots, if I didn't include the 0, then I would fill them in. But when we're multiplying, as we talked about earlier, we have to account for decimals once we've multiplied it out. Okay, 2 times 3, if there were no decimals, would be 6. But it's 0.2 by 0.3. So now I have 1, 2 decimal places. So I go, and I start here. And I go 1, 2. Now it's not 0.6. There's point blank 6. So in that blank spot, we fill in a 0. So the answer would be 0.06 or 0.06. So anytime there's blank spots to the right, we can fill in as many zeros as we want to pass a decimal number. We can call 1, we can write that as 1.0 or 1.00, I mean, it's all the same thing. We can continue on as far as we want to. If we ever end up with a number that's like this, and we have, let's say, 3 blank spots, well, we'd fill those in with zeros. So just kind of being aware of that in our equations that we come up with. These circle graphs or pie graphs or pie charts, we use these a lot to show parts of a whole. They're really nice if we're doing polling or surveying or just trying to get an overall sense of how people break down their time or in their day, or asking a group of people certain questions to see what their responses are. It just gives us an idea. So example 5 says Brett collected information from his classmates about their pets. He displayed the information about the number of pets in the circle graph. There was 16 dogs, 8 cats, 4 birds, and 4 fish. Okay, so how many pets are represented? Well, 16 plus 4 is 20, plus 4 is 24, plus 8 is 32. So there's 32 total pets. What fraction of the pets are birds? Well, 4 of our 32 total. So 4 out of 32 would reduce down to 1/8. Okay, and then what percent of the pets are dogs? Well, 16 of 32 is half. Or we can look at the chart and see, well, that's half of the circle. Half as a percent would be 50%. So that's where these are really nice to kind of visually just represent a large, set of numbers or data to show parts of the whole. It all adds up to one full circle or 100%. So we can use that to visually represent, if we're polling everyone in class, what's your favorite food, and all the different ones that came up there, we would break that down. Or how much time do you spend on homework or different things like that. We could get all those responses and then put it into a pie chart. Okay. Different examples of, we can show what represented in a bar graph or a line graph. We can also put those into circle graphs. So it just depends on what the information is and what we're trying to display. Sometimes different graphs, even though they can all show the same thing, it's sometimes better to use certain ones instead of others. Okay, practice set we'll do when we return. And that will be it. Our next class will be reviewing for a test. So make sure you come ready to go with questions, and we'll see you then.